Hello dears. Unit 2 or structure of atom is the topic in chemistry we are going to deal with, and NCERT Chemistry Solutions is what we are offering in this episode. This is Shishir Mittal from Vyas Edification, Kota. Welcome to the wonderful world of chemistry. I must add, before starting atomic structure, I must add, this is a very fundamental chapter which actually talks about how what is the structure of matter or how matter actually is made. What is the importance of this chapter? Actually, on this chapter, foundations of entire chemistry rests. There are more chapters like thermodynamics, yes, but ultimately, structure of atom is one of the key chapters which helps us in understanding why matter behaves the way it does. In that sense, it's a very fundamental chapter. There are portions in which you will need to actually learn certain definitions, certain properties, and there are sections in which you're supposed to analyze, see properly what is the concept, understand it, grasp it, and apply that. In that sense, this chapter is very, very vivid. It contains both memory-based ideas and it also contains a lot of deep understanding ideas and concepts, and let us explore all these using NCERT questions as an excuse. Let's begin. Calculate the mass of electrons, calculate the number of electrons which will together weigh 1 gram. Now, in this question, please remember that it is assumed that you are aware of mass of electron is so much. It is otherwise regarded as a standard data and you are just supposed to take this, so much is the mass of an electron. So what would I say? I would say that 9.1094 into 10 raised to minus 31 kilogram is the mass of 1 electron, right? But I need 1 gram, right? So let me convert kilogram to grams. 9.1094 into 10 raised to minus 31 into 10 raised to 3 grams. This one contains 1 electron? Yes. This makes it how much? 10 raised to minus 31 into 10 raised to 3 is 10 raised to minus 31 plus 3, which is 10 raised to minus 28, right? So 9.1094 into 10 raised to minus 28 grams contains 1 electron. So 1 gram would contain how many electrons? This into this upon this. How? Ratio and proportion, 600, simple. So 1 into 1. It is not e to the power minus s. Sorry, don't misunderstand this. What I mean to write is electrons, nothing else. What do I need to do? Now I just have to do calculations. And how would I do that? This is a little mathematical portion. Let me again share with you a secret. A secret? Yes. And what is that secret? It's a calculation secret which says 1 upon 1 plus x is approximately 1 minus x. And 1 upon 1 minus x is approximately 1 plus x if x is much, much less than 1. If there is a very small number being added or subtracted to 1, then 1 plus x, the reciprocal is approximately 1 minus x and vice versa. Now, I have borrowed this result from binomial theorem in maths. We have not studied that. It doesn't matter. It's a result from maths. Just take it. Fine. So, I could use this and calculate this dirty thing. I could say that this is 1 upon 0.91094 into 10 raised to minus 27. Yes. I'll take this calculation here and I'll write this is 10 raised to 27 divided by 1 minus some number. Can I just write down complement of this number? Yes, I believe I can. So that would be 0. Well, start from this 6, okay, and 0, 9, 8, and this should be 1, 0, 0. The 0.08906 into so much. And 1 upon 1 minus x is approximately 1 plus x, so this is approximately 1 plus 0.08 906 can be approximated as 1 into 10 raised to 27, which is 1.0891 into 10 raised to 27 plus 27. So many electrons must be present in 1 gram. I've done this with calculation because usually calculation is the problem. Let's check the accurate answer. 1.098 is the calculator answer, and 1.089, very close we have got, into 10 raised to 27. So I guess we have done a very good job even without using a calculator. Calculate the mass and charge of 1 mole of electrons. Now, this is very interesting. 1 mole of electrons. How much is 1 mole? 1 mole is 6.023 into 10 raised to 23 electrons. Right? What is the mass of 1 electron? Mass of 1 electron is 9.1 into 10 raised to minus 31 kg. Roughly, we just saw that, right? I mean, this is a constant, we can assume that. And therefore, mass of 1 mole electrons is 9.1 into 10 raised to minus 31 into 6.023 into 10 raised to 23. How lovely is that number? And what does that give me? If I just say 31 and 23, that makes it how much? And 9 6 would be 54. So this is 54.6, a little more than that, around 54.7 at best. 5.47 into 10 raised to 24 and 31 would make it 10 raised to minus 7 grams, or around 0.547 micrograms. Micro is 10 raised to minus 6. Let me remind you, micro is 10 raised to minus 6. So many micrograms. That's it. That is the mass of 1 mole of electrons, or this is the molar mass of electrons. Pretty small. Yes, we know that. Anything else? Yups. Let's see. What about charge of 1 mole electrons? Now, charge on 1 electron is 1.6 into 10 raised to minus 19 coulombs, approximately. So, charge on 1 mole electrons, and charge on 1 mole electrons, it also has a special name. It is called 1 Faraday. It is in honor of a great scientist, Michael Faraday. So, we say this is 1 Faraday. We have not studied Faraday. We have not studied Faraday. Don't be afraid. It is just a name. Faraday is a dead man, and a very respected dead man. So don't be afraid of him. He's a very nice, very benevolent, and very superb scientist. One of the most respected scientists in the history of science. So charge on 1 mole of electrons, which is also called 1 Faraday, that would be equal to charge on 1 electron into Avogadro's number. Let's multiply that. How much is that? 16 3s are 48, 16 2s are 32, 36, 16 6 are 96. How lovely is that? Yes. So that would give me 9.64 approximately into 10 raised to how much? Well, 19 and 23, that makes it 4 coulombs. Well, 1, 2, 3, 4. Let's jump this. This is 96368 coulombs. Huge number. So this is the accurate value of 1 Faraday. Often people approximate it as 96500 coulombs also, but that is just an approximation. These are the charges and mass. These are the charge and mass carried by 1 mole of electrons. Calculator answers mass of 1 mole of electrons and mass of charge on 1 mole of electrons. Just let's compare 5.486 and 5.4 7, we are close by, not very ugly, है ना? And 9.647, 9.637, we are close by. Again, I would say beautiful it is. Well, calculate the total number of electrons present in 1 mole of methane. What is methane? Methane is CH4. Carbon contains 6 electrons and hydrogen contains 1 each. So I have 10 electrons. Okay. So every molecule of methane contains 10 electrons. Why exactly? Carbon personally contains 6 electrons and each hydrogen contains 1. So if we add up CH4, that makes it 6 plus 1 plus 1 plus 1 plus 1, 10 electrons. Perfect. So 1 mole of methane. Now 1 molecule of methane contains 10 electrons. So 1 mole methane molecules will contain how many electrons? Well, that would be 10 into Avogadro's number, which is 10 into 6.023 into 10 raised to 23, which is 6.023 into 10 raised to 24 electrons. Wonderful. That's it. Lovely. Find A, the total number, and B, the total mass of neutrons in 7 milligrams of C14. Assume that mass of a neutron is so much. Oh my God, what do? We solve. And how exactly? See, we have 7 milligrams of C14. Now, what is C14? C14 represents, it has 6 protons. Yes. How do I know this? You have to mug this up, that carbon contains 6 protons, or anything that contains 6 protons in the nucleus is called carbon. You have to remember this as a student of chemistry. This data will not be given to you every time. Anything with atomic number 6 is called carbon. And 14 is atomic mass number, so neutron plus proton is 14, but protons is 6. Therefore, number of neutrons is 14 minus 6, which is 8. So 1 atom of carbon contains 8 neutrons. 8, right? Now I have 7 milligrams of C14. How do I find this number and mass? I need to first find number of moles, right? So number of moles of C14 atoms. Now moles is mass by atomic mass. Yes. So moles will be mass. Mass is 7 milligrams divided by atomic mass. Now atomic mass 14. It is given clearly, so it is 14 grams per mole. That makes it 0.5 millimole. Why milli? Because milligrams will give you millimoles. Milli just means multiplied by 10 raised to minus 3, nothing else. Don't worry about it too much. So I have 0.5 millimoles, which means 0.5 into 10 raised to minus 3 moles of C14 atoms. So I have got number of C14 atoms. But is this what I need? No. I need number of neutrons. Okay. Now, therefore, number of moles of neutrons is how much? It is something like, if I have one truck, and one special truck which contains 8 wheels, a giant truck which contains 8 wheels. Fine. So if I have 10 trucks, how many wheels would I have? Well, just multiply 10 by 8, because every truck contains 8 wheels. So if you have 10 trucks, you have 10 into 8, that means 80 wheels. In the same fashion, if I have one atom that contains 8 neutrons, if I have so many atoms, then number of neutrons will be 8. 8 is number of neutrons present in one atom multiplied by number of moles of atoms, that is 4 millimoles of neutrons. but they have wanted not the moles but number. And I use the formula N is Avogadro's number into number of moles. Number of atoms or molecules is Avogadro's number into number of moles of that substance. Avogadro's number as a unit per mole, and this becomes mole. They can cancel away. How much do I get? I get, well, let's multiply by 4. So 23 4s are 92. So 24.092 into 10 raised to 20. Or I could say this would be 2.04. No, I'm sorry. That would be 2.4. 2.4092 into 10 raised to 21 neutrons. We should write it in scientific notation. This would be the number of neutrons, right? And they are now expecting the mass of a neutron also. They have given mass of neutron and they expect the total mass. How do I calculate that? Well, I don't think that's very difficult, because if I've got the number of neutrons, I can multiply this by mass of a neutron. Yes. What would I get? Mass of neutrons. There are two ways I can do this. I'm doing it by the more stupid way. 2.4092 into 10 raised to 21 neutrons. And how many neutrons do I have? Yeah, what is the mass of a neutron? 1.675 into 10 raised to minus 27 kg. Fanciful. Let us multiply this and get a really dirty number, and that would be the answer. That is one method of doing that. You can calculate that and see this is the answer. This is number of neutrons. We have got a number 2.408, and this is what we did by hand calculations, 2.409. That is more accurate. This is what I get into 10 raised to 21 neutrons. What about the mass? Well, mass comes out to be this much. If you multiply that number, you get this ugly thing. And can I just stress that you can do it? I told you this is a stupid way of doing it. I can give you a simpler method also. What? See, mass number is 14. That means mass of one C14 atom is 14 AMU, right? Mass is 14 AMU, and this mass is because of neutrons, protons and electrons. Electrons are negligible, so essentially this is mass of neutrons plus protons. If I may be so bold and a little approximate, I say it is a little approximate, but if I may be so bold, I could say that, see, out of 14 AMU, mass of neutrons is 8, because we calculated it as 6 protons and 8 neutrons. So 14 AMU mass of C14 contains the 14 AMU mass. If you take of C14, one atom of Cu14, 14 AMU its mass, it contains 8 AMU neutrons. That means, therefore, 14 grams of C14 contains 8 grams neutrons, right? That means that if I have 7 milligrams of C14, it contains 7 milligrams into 8 upon 14 of neutrons. If you take grams, grams will cancel off. That's it, yeah. So that is 4 milligrams of neutrons. Of course, this is approximate answer. You can cross-check very easily. 4 milligrams of neutrons should be there. An accurate answer would be obtained if you multiply that number of neutrons by mass of each neutron, and then you get 4.035, whatever. That's as close as it gets. Find the total number and total mass of protons in 34 milligrams of ammonia at STP. Will the answer change if the temperature and pressure are changed? Well, let's take a look. Now, we have to find the number and total mass of protons in 34 milligrams. So, what is given? I am given that mass of ammonia is 34 milligrams. Now, NH3, nitrogen is 14, hydrogen is 1. So, ammonia's molar mass would be 14 plus 1 into 3. That is 17 grams per mole. This is molar mass of ammonia. Yes. Can I find the number of moles of ammonia? Yes. So, moles of ammonia molecules is this is by formula it would be mass by molar mass, which is 34 milligrams divided by 17 grams per mole. Grams cancels away, that makes it 2 millimoles. Please note, milli does not get cancelled with grams. Milli simply means multiplied by 10 to the minus 3 and nothing else. That stays. So I have 2 millimoles of ammonia, and one nitrogen atom contains 7 protons. Why? That is the definition of nitrogen atom. Any nucleus that contains 7 protons would be called nitrogen. From periodic table we know that. Otherwise you should know that H atom contains 1 proton. So NH3 contains 7 plus 1 into 3, that means 10 protons. Wow. So I have 20 millimoles of NH3 molecules, and this implies 2 into 10 millimoles of protons. So I have 20 millimoles of protons present in ammonia. Now I have to find number and I have to find mass. How can I find the number? Number is quite simple. I can say number of protons, N, is moles into Avogadro's number. Moles is 2, 20 millimoles. So many moles into 6.023 into 10 raised to 23 per mole. Well, let's multiply that. What would that give? 12046. And what about the decimal? 120. That means 1.2 into 10 raised to 22 protons. So my dear, this is the number of protons. Just multiply and get that number. Anything else? B part, total mass of protons. How do I get the mass of protons? Well, that's very simple again. See, I'll use the space for further calculations. Now, nitrogen atoms, if you see, and a hydrogen atom is 1, 1. Mass of hydrogen is same as mass of a proton. Electrons have negligible mass. And whatever is the mass of nitrogen, if nitrogen has a mass of 14, then out of that protons have a mass of 7 AMU, and remaining 7 AMU goes for the mass of neutrons approximately. Very, very approximate. Not very closely. It is reasonably accurate, but a little approximate. So, mass of protons in ammonia is 10 AMU. One molecule of ammonia. Why? 7 AMU is the mass of protons in nitrogen, 1 AMU in each hydrogen. There are 3 hydrogens, so 7 plus 3, 10 AMU. Okay. Therefore, 10 AMU. Now, 1 AMU per particle is equal to 1 gram per mole by definition. So therefore 10 AMU per molecule is equal to 10 grams per mole of ammonia molecules. If I take ammonia molecules, 1 mole of ammonia molecule contains 10 grams of protons. But do I have the number of moles of ammonia molecules? Yes, I have that. It is how much? 2 millimoles. So therefore, 1 mole of ammonia molecule contains 10 grams of proton, so 2 millimoles of ammonia molecules multiplies by 10 grams of protons per mole of ammonia molecules. I have written units very clearly so that you can just cancel this. So I get how much? This is 20 milligrams of protons, or 2 into 10 raised to minus how much? If you just want to calculate in kilograms, then milligram is 10 raised to minus 6 kilograms, so 2 into 10 raised to minus 5 kilograms of protons. Okay, so much so? Yes, so much so. If you don't want this, then you use the accurate mass of protons and do the multiplication, you will get very nearly the same number. See, if you see the mass of protons, this is what you get. And will the answer change if temperature and pressure are changed? The question is, I'm sorry, it will not change. Why? Because mass is independent of temperature and pressure. So, no. You may say that the calculator answer is not exactly 2, but it is 2.018. How do I get this 2.018? I can tell you that also. Just look. Now, if you want to be more accurate, I can tell you a method. Mass of one proton is 1.0073 AMU accurately, more accurately rather. Hai na? We approximated it as 1 AMU. But actually mass of one proton is not 1 but 1.0073. If you want to take the tail of 0073 and drag it along, you can get a more accurate answer. How exactly? I'll show you. So let me recalculate in a more accurate fashion. Wherever we used 1, now we had 2 millimoles. 2 millimoles of ammonia will correspond to 2 into 10 into 1.0073 milligrams of ammonia. So our answer gets multiplied by 1.0073. So that stupid 0073 gives me additional glamour. So how much that comes out to be? This is 2.0146 into 10 raised to minus 5 kg. So many grams, if you convert to kg, this is what you would get. So approximate answer was 2 into 10 raised to minus 5 kg. You want to come more close in decimals, 2.0146, 2.01 ting ting 38. That's close. It's a more accurate answer. If you want, you can use this result, but for this, you have to learn that mass of one proton accurately is 1.0073 AMU. How many neutrons and protons are there in the following nuclei? How many? Let's see. We have carbon, oxygen, magnesium, iron and strontium. Okay, that's lovely. And how do I find number of protons? This number, you know, the number below, this is called, just if you have any element E, then the number here is number of protons. And the number on the top is neutrons plus protons. It is called mass number and this is called atomic number. We were supposed to find neutrons and protons. How can I find this? I can simply find this. I'll just make a small table for you. I don't have space here, so I'll solve it on the top. This is neutrons, protons and neutrons. Protons and neutrons. How many protons? This number, 8, 12, 26, 38. These are the number of protons, or 6 for that matter, for carbon, right? What about neutrons? Now, this is neutron plus proton is 13. So, neutron is 13 minus protons. So, 13 minus 6, which is 7. So, I have 7 neutrons here. Neutron is A minus Z. This is A, this is Z. Neutrons is A minus Z. So 16 minus 8, 24 minus 12, 56 minus 26, 88 minus 38, which is 50. Neutrons and protons. This is the numbers here, and that's it. Write the complete symbol of the atom with the given atomic number Z and atomic mass A. Well, that's not very troublesome. First, you have to decide element based upon the atomic number Z and atomic number Z. Actually, it will be very helpful if you remember the atomic numbers of noble gases. Noble gases, yes. Like it is helium, neon, argon, krypton, xenon and radon. The way I remember it, it is 2, 10. What about argon? 18, 36, 54 and 86. This is the group plus 8, plus 8, plus 18, plus 18, plus 32. 8, 8, 18, 18, 32. You add this and you get the entire series. 17 means just before argon. And that would be a halogen. Yes, that is actually chlorine. Wow. So chlorine, 1735. That's how we write this. Z goes below and atomic number goes above. Like this. You have any element? You write A here and you write Z here. That's the standard way of writing it. 92, oh my God, this is so enormous. What is 92? 92 is uranium. Fancy. U-233. Uranium is the heaviest element, atomic number 92, which is available in nature. The heavier are still there, but they are not naturally found. They are artificially synthesized in laboratories. Z4, atomic number 4, hydrogen, helium, lithium, and fourth is beryllium. Yes, so it is beryllium. 94. Wow. Every atomic number is associated with an element. And that element has a specific name which we have to memorize. Otherwise, there is no way you can figure out that atomic number 4 means beryllium. You have to do this from learning periodic table. Yellow light emitted from a sodium lamp has a wavelength lambda of 580 nanometers. Calculate the frequency and wave number of the yellow light. How do we do this? See, wavelength lambda is given to me as 580 nanometer. Fine. Wave number nu bar is simply 1 by lambda, which is 1 upon 580 nanometers. We just to calculate this. That would be the wave number. Okay. What about the frequency? Frequency is now Velocity of light is frequency into wavelength. Now, velocity of light is fixed 3 lakh kilometers per second. So, frequency nu would be c by lambda. C is 3 lakh kilometers per second. 3 into 10 to 8 meters per second by lambda. How much is lambda? Lambda is lovely 580 nanometer. Nano is 10 to minus 9, don't forget that. That makes it 3 into minus 9, 3 by 5.8 into 10 raised to 15 per second. Okay, that's very interesting. That would be around 5.3, 5.2, something like that, into 10 raised to 14. 5 point something into 10 raised to 14 per second. We can calculate that. 5.17 into 10 raised to 14 per second. That is the accurate answer. And the wave number, you take a reciprocal. This is what you get. But we had it in nanometer. If you want me to convert nanometers to meters, I'll do that for you. Nanometer is 580 into 10 raised to minus 9 meter. Right? 1, 2, 3 decimals I can shift. 1 upon 0.58 into 10 raised to 6 per meter. Nano gets removed. Yeah. 1 upon 0.58. And how much is that? That is 1.72 into 10 raised to 6 per meter. That, my dears, is the wave number. Find the energy of each of the photons which correspond to light of frequency 3 into 10 raised to 15 hertz. How much is that going to be? Let's take a look. See, E by Planck's quantum theory is h nu. 6.626 into 10 raised to minus 34 joules second into 3 into 10 raised to 15 hertz mean per second. I just have to multiply this by 3. 18, 7, 18, 19. So 15 and 16. 16 and 34. That makes it 1.9878 into 10 raised to minus 18 joules. 1.9878 into 10 raised to minus 18 joules. That is the loving answer here. Energy of photons which have a wavelength of 0.5 angstrom units. Now, energy E is h nu, which is also hc by lambda. Lovely. This is 6.626 into 10 raised to minus 34 joule second into 3 point nothing into 10 raised to minus, so plus 8 meters per second. These are constants actually. And what is lambda? It is 0.5 into 10 raised to minus 10 meters. Can I find this? Of course I could find this in joules. Meter gets cancelled, per second gets cancelled. This is awfully ugly. We just multiplied by 3 and more multiplied by 6 rather. 3 by 0.5 is 6. So 6 is 36, 6 2 is 18, 21, 36, 38, 36, 39. Oh, this is heavy. This much into how much? How many decimals? Into 10 raised to 34 minus 34 plus 18. That is, may say 10 to minus 16 joules. Oh, that's heavy. So that would be 3.9816 into 10 raised to minus 15 joules. That would be the energy of every photon. 3.98 into 10 raised to minus 15 joules. This is where we landed up. And that's what is the answer. Calculate the wavelength, frequency and wave number of light wave whose period is 2 into 10 raised to minus 10 seconds. That's as lovely as it gets. Period. Tau is 1 by frequency mu. That's how I define it. So, frequency nu is 1 by period, which is 1 by 2 into 10 raised to minus 10 second, which is 10 raised to 10 by 2 per second, which is 5 into 10 raised to 9 per second, which is 5 into 10 raised to 9 per second. How much is that? That is the frequency of light wave. Now next comes wavelength and wave number. Wave number is just reciprocal of wavelength, so I'm just supposed to find essentially either one of these. I mean, the other one would be automatically there. Now, C is lambda nu. Okay. What does that mean? The wavelength lambda is C by nu, which is C into tau. 1 by nu is tau, period. C is 3 lakh kilometers per second. And period is how much? I'm given that directly. It is 2 into 10 raised to minus 10 seconds. Oh my God. Cut this short. How much is this? This comes out to be 0.06. Oh, this is huge. 0.06 meters. Yes. And what about wave number? Nu bar is 1 by lambda. 16.67 per meter. That comes out with a huge, huge wavelength. And this is where I get. Let me check the regular answers. You can see these are the ones. What is the number of photons of light with a wavelength of 4000 picometer that provide 1 joule of energy? How can we handle this? Well, we have to find number of photons, fine, and they should have 1 joule of energy. Now, typically, do you remember what is the magnitude of energy for 1 photon? Is it around 1 joule? No, it's very less, around 10 minus 15, 16, 17, 18, 19 joules. I mean, it's very, very small amount. So that means there have to be many, many, photons which are combining together to give you 1 joule of energy. And I'm having, the photons of wavelength 400 picometer. So let me do this. Let me find out energy of 1 photon, right? So energy of 1 photon E is hc by lambda, right? Which is 6.626 into 10 raised to minus 34 joules second. 3 into 10 raised to 8 meters per second by lambda. How much is this lovely lambda? It is 4000 picometer. Please see, I am cancelling the units as if I am cancelling the numbers, and that's very important. How much does that give me? Well, 3 zeros gone. This stands to 5. Now, 10 raised to 5 and 12, that makes it 10 raised to, let me not write it like this, it becomes ugly and confusing. I'll just write it together. This is 10 raised to minus 9. If I cut away this 0 and this, and 9 and 8 make it 17. So 10 raised to 17 and 34. This portion, this, and this, we can dissolve them together. How much do I get? I get 20 minus 14 minus 17. So 6.626 into 3 by 4 into 10 raised to minus 17 joules. Okay, this is what you get? Yes, this is what we seemingly get. Fine. Just check once. 20. Yeah, the minus 14, 15, 16, 17. Yes. Now, we need total 1 joule. So, number of photons into energy of each photon is total energy. How do you get common sense? If I take 1 photon, fine. I take 2, 3, 4, just add up their energies, and repeated addition is multiplication. So if I just take number of photons, multiply this by energy of each photon, I'll get total energy. Yes. Therefore, number of photons is total energy, which is 1 joule divided by energy of each photon. How much is this? I have not even multiplied it. 6.626 into 3 by 4 into 10 raised to minus 27. No, sorry, 10 raised to minus 17. 10 raised to minus 17 joules. Okay. Joules cancel away. That's loving. How much do I get? Well, some lovely number. 1 by, now, this is 4 ones are 4, 26, 4, 6 are 24, 22, 4, 5 are 20, 26, 4, 6 are 24 into 3. Now, this is going to look very ugly. It is not. Actually, this is convenient. Let's just multiply by 3 and see. 10 raised to 17 by 5 is 15, 6 is 18, 19, 15, 16, 18, 19, and this is what I get. How much is this? It's close to 5. If you're not very bad about it, if you don't feel very strongly, I can say this is roughly 5. It is 5. So this will be approximately 2 into 10 raised to 16. The number comes out to be 2 into 10 raised to 16. As a matter of fact, it is going to be a little more than 2. 2.012 into 10 raised to 16 photons. And that is the calculated answer. Now, this is a question about photoelectric effect. It says, a photon of wavelength 4 into 10 minus 7 meter strikes on a metal surface. So let me note down the data. It says, lambda is how much? 4 into 10 to minus 7 meter. Work function of the metal being 2.13 electron volts. Okay. Work function is 2.13 electron volts. Calculate, 1, the energy of photon in electron volts, and there are many things to calculate, it seems. First of all, energy of photoelectron, first of all we have to calculate simply energy of photon in electron volts. Now, energy of photon is hc by lambda. Wow, yes. Now, do you realize that if I substitute standard SI units, I would get some number, of course. But also, do you realize that 1 electron volt is 1.6 into 10 to the minus 19 joules. Okay. Well, if I dare use this conversion, can I directly substitute for h, c, this constant also, and get some number which is an easier number to handle? What do I mean? I'll just show you. First, let me do it by routine method, and then I'll tell you shortcut. 6.626 into 10 to minus 34 joule second. 3 into 10 to 8 meters per second. We know that by lambda. The lambda is, say, 4,000 angstrom units, na? In this case. 4 into 10 minus 7 meter, which is 4,000 angstrom units. Let me say it is 1,000 angstrom units. What? Let me just say it. Just believe it. Believe me. Hai na? It's some number in angstrom units. Hai na? Let's say it is 1 angstrom unit. Just for the sake of simplicity. I'm not saying in our question lambda is 1. I'm saying let us assume that we are considering a case if lambda is equal to 1 angstrom unit. And if you're not happy, just keep it as lambda angstrom unit, whatever. Hai na? I get. So I'll get some number as energy of photon. How much is this going to be? Well, what I'm supposed to substitute not in terms of angstrom units here, but in terms of meters. So 1 angstrom unit would mean 10 raised to minus 10 meters. Meters simply get cancelled here. That's fine. This is what I get. How much is this? 6.626 into 3 into 10 raised to minus 16 joules. Right? Right. Now, this is energy of 1 photon. Can I calculate this in terms of electron volts? Yes. This would correspond to 6.626 into 3 into 10 raised to minus 16 upon 1.6 into 10 raised to minus 19 electron volts. How much is this? How much is this? Just can we calculate that? Yes, we can easily do that and we can get the number. And this is 1 2424, I mean, just these three numbers together into, this is 10 raised to 3 into 10 raised to 4. Oh my God, how much is this? ये हो जाएगा 1 2 का 4 और फिर से 2 4, 1 2 4 2 4, 1 2 4 2 4 इलेक्ट्रॉन वोल्ट्स। ठीक, अगर ये सारी गंदगी अपन सॉल्व कर लें तो अब लैम्डा अगर 1 की बजाय, अगर लैम्डा अगर 1 की बजाय 4000 आ जाए तो क्या होगा? तो हमने एक एक्सप्रेशन निकाली एक तरह से, कौन सा? एनर्जी ऑफ फोटोन। आई जस्ट राइट इट फॉर यू। एनर्जी ऑफ फोटोन is 1 2 का 4 2 4 अपॉन लैम्डा इन एंगस्ट्रॉम यूनिट्स, इतने इलेक्ट्रॉन वोल्ट्स। ऐसे तो जैसे हमारे केस में लैम्डा कितनी आ रही है? हमारे केस में लैम्डा आ रही है 4000, तो हम कहेंगे एनर्जी ऑफ फोटोन विल बी 1 2 का 4 2 4 अपॉन 4000, इतने इलेक्ट्रॉन वोल्ट्स हैं। और डिवाइड करना 4000 से, इज वेरी सिंपल। 3 इधर गए, 1 2 3, ओके, 4 3 सा 12, 4 1 सा 4, 4 से इतने इलेक्ट्रॉन वोल्ट्स। दैट्स इट, दैट्स इट। अच्छा, तो ये क्या आपने तो सब बोला, हम कंफ्यूज हो गए। आप तो आंसर देखो पहले, तो मैच कराओ, बढ़िया मस्त। 3.10 इलेक्ट्रॉन वोल्ट्स, यस, परफेक्ट। कैलकुलेशन क्या करी थी एक बार फिर बताता हूं मैं आपको। कौन सा? एनर्जी ऑफ फोटोन is 1 2 का 4 2 4 अपॉन लैम्डा इन एंगस्ट्रॉम यूनिट्स। अगर आप ये फॉर्मूला याद रख लें तो बार बार H और C मल्टीप्लाई करना, जूल्स का इलेक्ट्रॉन वोल्ट में कन्वर्जन, वो सब हमने ऑलरेडी कैलकुलेट करके यहां कर लिया है। उस मेहनत से आप बच जाएंगे, ऐसे आ जाएगा। ये बहुत इजी है, बहुत अच्छा है। ठीक, इससे हमने निकाला 3.1 लगभग इलेक्ट्रॉन वोल्ट्स। कौन सा था? एनर्जी ऑफ फोटोन। ठीक है सर, तो ये तो फोटोन की एनर्जी है जो मेटल पर आ रहा है। ये है मेटल, हाँ, इस पे फोटोन आया, मस्त। ठीक, 3.1 इलेक्ट्रॉन वोल्ट का, और फोटो इलेक्ट्रॉन निकले। तो एनर्जी ऑफ फोटो इलेक्ट्रॉन कितनी होगी? काइनेटिक एनर्जी ऑफ एमिशन। काइनेटिक एनर्जी ऑफ एमिशन इज इंसिडेंट एनर्जी, एनर्जी ऑफ फोटोन माइनस वर्क फंक्शन। 3.1 माइनस 2.13 विच इज कितना? वेल 3.1 में से 2.1 तो 0.97। सॉरी, यहां आएगा डेसिमल। 0.97 इलेक्ट्रॉन वोल्ट, ये है काइनेटिक एनर्जी ऑफ फोटो इलेक्ट्रॉन्स। 0.97 इलेक्ट्रॉन वोल्ट्स। कुछ और हसरत बाकी है? जी हाँ, वेलोसिटी ऑफ फोटो इलेक्ट्रॉन। हो ये कैसे निकालेंगे? बड़ा आसान है। काइनेटिक एनर्जी इज हाफ mv²। अच्छा, तो वेलोसिटी इज 2 टाइम्स काइनेटिक एनर्जी अपॉन मास की गंदी वाली रूट। अच्छा, सो व्हाट अबाउट द वेलोसिटी? वेलोसिटी इज √2 ek/m। यस, how much is this going to be? 2 times kinetic energy of photoelectrons. Now we know that we had 0.97 electron volt into, now 1 electron volt is 1.6 into 10 raised to minus 19 joules. Well, fancifully yes, by mass. Now mass of electron is 9.1 into 10 raised to minus 31 kg. Okay, yes. How much does this fanciful value give you? Actually, if you understand 2m and this conversion factor, they are all very common. They will always repeat themselves. So I'll just calculate, tell you, and let us learn that as a formula because we will need that very often. Let's do that. So as you calculated, it comes out to be 5.916 root of kinetic energy in electron volts. So many meters per second. Oh wow, of course, into 10 raised to 5. 5.9 5.16 or 5.92, whatever, into 10 raised to 5 root of kinetic energy meters per second. If you want, you can simply take this as a formula also. This is velocity of photoelectron. The velocity of photoelectron will be, in our case, this is 0.97 electron volts. That is the kinetic energy. We take a root of that and multiply, we would get 5.83 into 10 raised to 5 meters per second. This is what we will get, right? These are the official answers. We are very close to that. That's perfectly all right. Well, this is a question which mentions something funny. It talks about ionization energy. Let's see what it says. Electromagnetic radiation of wavelength 242 nanometers is just sufficient to ionize the sodium atom. That means it gives you just sufficient energy so that electron from sodium atom can just run away. Calculate the ionization energy of sodium. That is as good as the energy of photon, right? So in kilojoules per mole, that is really impressive. We have wavelength of 242 nanometers. Now energy E is hc by lambda, right? So let's just do that. H is, and as a matter of fact, if you want, you can also find this in electron volts and then use a conversion of how much 1 electron volt per photon converts into kilojoules per mole. 1 electron volt per photon is 1.6 into 10 raised to minus 19 joules into 6.023 into 10 raised to 23 per mole. This is 1.602 into 6.023 into 10 kilojoules per mole. So 1 electron volt per photon can be converted like this also. Okay. And we remember we had a formula. This is 1 2 ka 424 upon lambda electron volts per angstrom units. Right? If you remember that, it is 1 2 ka 424 upon 242 nanometers. That is, if we convert this to angstrom units, this will be 2420 angstrom units. So many electron volts. Right? Fine. Let's calculate that. This is energy of 1 photon. This is per photon. And this corresponds to, if you have a multiplication factor here, we can simply multiply and get the answer. Right? Let's see what is the factor. On calculation, my dears, if you see, this conversion factor comes out to be, and this is very important, 96.47 kilojoules per mole. You must remember this very clearly. This is 1 electron volt per photon. Yeah, per particle. It's not per mole. That is 96.47 kilojoules per mole. People forget Avogadro's number and give wrong answers. One has to be very careful there. And this would be around how much? 12 to the 24, it would be around 5 point something. If you just calculate, that would be 5.133 electron volts. And that would, electron volts per photon, of course. And that would correspond to, if you multiply them happily, that would be around 495 kilojoules per mole. Wow. 495 kilojoules per mole. Yes, my dears, this would be the ionization energy of sodium as per this data. A 25 watt bulb contains a monochromatic means which has same wavelength, all photons are same, yellow light of wavelength 0.57 micrometers. God bless him. Calculate the rate of emission of quanta per second. What does that mean? That means, what is the rate of emission? It means how many, what is the number of photons emitted per second. Now, 25 watts means 25 joules per second. Fine. So this is 25 joules is total energy. That means energy of 1 photon multiplied by number of photons per second this will give me 25 joules per second, right? That's easy. I'm supposed to find number of photons per second. Photons are quantas, so number of quantas per second. Per second means rate of emission. So I just have to find energy of one photon. How much is that? Could I find that? Yes, I guess I can. E as forever is hc by lambda, 6.626 into 10 raised to minus 34 joules second into 3 into 10 raised to 8 meters per second by the stupid lambda, which is how much? 0.57 into 10 raised to minus 6 meter. Micro means 10 to minus 6. Oh wow, what do I need to do? Calculate, just feel happy about it. Or just substitute. How much is this? This is 6.626 into, now 17 3s are 57. Let me just at least cancel out a few things. Let's say it is divided by 0.17. I have this number and this number. And this is 14, 10 is to 14 and 34. That makes it into 10 to minus 20 joules. Pretty interesting. Let me substitute this here. Therefore, number of photons per second is equal to 25 joules per second divided by this gandh. What is this? 6.626 into 10 raised to minus 20 into 0.17 joules. Okay, lovely. How much is this? Multiply, divide, just feel happy about this. 10 is to 20 into 25 into 0.17, 6.626, something in terms to 19 per second. These would be the number of photons emitted per second. And how much would this come out to be? Well, I think we have some number. It is 7.17 into 10 to 19. You calculate that accurately and you get that. But how can we calculate by hand? You have means. If you want, I can help you with calculations also, rough calculations that is. Well, if I just look at 25, that does give me some feelings. 25 4za is 100. So let me multiply and divide by 4. So 25 into 4 is 100. 100 into 0.17 is just plain 17. So I have 17 divided by, what is this? This number into 4. 25, say 25 into 4 would be 100. And 6, 4 6 are 24. And 24, 25, 26. So this is what I seemingly get. 17 by 26.5, roughly, closely. That does not sound like a very encouraging number. Let me just say, is it not very approximately? A little more than 17 is 18. A little more than 26.5 is 27. 18 by 27 is 2 by 3. That is 0.67. 6.7 something. And actually, what I've done is, I've just tweaked it a little. So it's around 6.7 something and 7.1. Now you can say 6 and 7 is different. We have made drastic approximations, of course, but if you just are a little more accurate, you would get what you need, 7.17. It's a rough calculation check so that our number is close to the correct answer. Yes, it makes sense. Electrons are emitted with zero velocity, okay, from a metal surface when it is exposed to radiation of wavelength 6800 angstrom units, okay. So this is the threshold wavelength, it means. Calculate the threshold frequency. The threshold wavelength lambda naught has been given to me as 6800 angstrom unit. Nu naught is question mark and work function is question mark. It is as simple as it gets. These are photons, right? The work function will be simply hc by lambda naught, which is 1,2,4,24 upon angstrom unit में 6800. So many electron volts. I just have to calculate this. It's become ugly. I'll just clean this up. I'm using a formula, that's it. This will give me the work function. How much would this come out to be? Well, let's check. 0.24. Now, 68 2za That would be 134, 136, 136, okay, minus how much? 12, 11.76. This is 2. I'm just trying to be clean in calculation. Minus 11.76 by 68. Now 11.76 is close to 12. 12 5s are 60. It's roughly 5.5. This is 0.18. This is approximately 2 minus 0.18, which would be 1.82. Okay, fine. So this would be around 1.82 electron volts, very closely. This is going to be the photoelectric work function of metal, around 1.82 electron volts. I have been given this in joules, but if you convert electron volts, this is what we would get, right? What about the threshold frequency nu naught? How can you get nu naught? Now, C is equal to lambda nu. So this is C by lambda naught. 3 into 10 raised to 8 meters per second divided by 6800 into 10 raised to minus 10 meters. As beautiful as it gets. How much? Well, 3 by 0.68 into 10 raised to 1, 2, 3, 4, minus 6, 6, 14 per second. 0.68, if I approximate it by 0.6666, it's approximately 2 by 3. So 3 upon 2 by 3, that is 9 by, that's 4.5. So around 4.5 into 10 raised to 14, and the accurate answer is 4.41 into 10 raised to 14. Yes, there we are. So this, my dears, is a presentation of all the solutions of NCERT atomic structure first part, which covers all the questions pertaining to Planck's quantum theory, of course, some basics, then quantum theory, and then photoelectric effect.